There it is. Okay, I'm going to have to go back and fix that. All right, now we have audio. The molecular formula, if you get into chemistry, you'll know just by looking at what atoms they are, whether they are ionically bonded or covalently bonded. But for the purposes of this class, H2 and O2 tell you nothing but the presence of 2 hydrogens or the presence of 2 oxygens. Okay, talking about chemical reactions. Now we are going to start to manipulate individual atoms, manipulate molecules, manipulate compounds. A chemical reaction is illustrated here at the bottom of the slide. We always see molecules, atoms, or compounds on the left, and then an arrow pointing to the right. Reactants and products are the 2 things that are part of a chemical reaction. Reactants are the molecules before the reaction starts or to the left of the arrow. Products are the molecules resulting from the chemical reaction or the molecules to the right of the arrow. Okay, so reactants are on the left, products are on the right. And this particular equation is a one-way equation. It only proceeds from left to right. Sometimes you will see a double-sided arrow, meaning that the products can also turn back into the reactants. But I don't see that double-sided arrow, which means molecule AB, when it's added to molecule CD, will go into molecule AC, leaving B and D by themselves out in the cold. That's how you read that chemical reaction. How do we control chemical reactions? And when we say the word control, we're basically saying, are we going to speed them up or slow them down? That's about all the control you get on a chemical reaction. So these 3 things given here, temperature, concentration of reactants and products, and catalysts, are ways of either speeding up or slowing down a chemical reaction. So temperature first. Heat is energy. We talked a little bit about that. Energy takes many forms. Heat is one of them. Okay? Heat, when you pump heat into a reaction, you pump energy into a reaction. So when we heat the reactants, we generally increase the rate of reaction. AB plus CD will then go faster into AC plus B plus D. Okay? And the opposite is true. If you cool a reaction down, that will also slow the reaction down. Concentration of reactants and products. So this is defined as an increase in the amount of reactants, generally increases the rate of reaction. An everyday example of this would be building a house. Okay? The reactants in building a house are wood, drywall, wiring, plumbing, nails, screws. Okay? Those are the reactants. The product is a house. If you have to sit around all day and wait for more drywall and wait for more plumbing, and then next week the wiring goes in, then the house is going to go up very, very slowly. But if you have all the wood, all the drywall, all the nails, all the plumbing, all the wiring that you need, the house will go up as fast as people can build it. Same thing with chemical reactions. If you have to sit and wait for oxygen or wait for hydrogen or wait for carbon because they're in very low concentrations, the chemical reaction will proceed slowly. But if you have all the carbon, all the hydrogen, all the oxygen that you need, then we can put them together as fast as we can, and that speeds the rate of reaction. So the concentration of the starting products, how much or how little there is, will influence the rate of reaction. And the last one are catalysts. Catalysts can influence the rate of reaction without directly influencing the reactants or products. And basically, they have a capability to decrease the energy needed to complete the reaction. If we just throw some arbitrary numbers at it, let's say for A to get to B, we need an energy of 10. But if the catalyst is present, then from A to get to B, we only need an energy of 5. So catalysts can do various things that help lower the energy that's needed in that reaction. And if that's too vague, if you want a specific example, if we go back to this slide, let's say A, B, C, D. The bond between A and B needs to be broken, and the bond between C and D needs to be broken if then A and C are going to bond. One thing a catalyst might do is grab a hold of A and B and bend them and put a lot of stress on that bond so that when we go to break that bond, it becomes very easy. Okay, so catalysts can do things like that. They can put extra strains on a bond that make it easier to break, and therefore lowering the amount of effort that we need to put in to break those bonds. That's an example of something a catalyst can do. Okay, we're going to start talking about different properties in our environment. One of them is water. Water is an incredibly important compound. Remember, it's hydrogen and oxygen in your environment and in your body. So water exists in a liquid form at a relatively low temperature. Most other compounds will turn into a solid at temperatures at which water is still a liquid. What temperature will water turn into a solid? 32 degrees Fahrenheit or 0 degrees Celsius. 32 degrees Fahrenheit or 0 degrees Celsius is the temperature at which water will go from a liquid to a solid. Most other compounds in liquid form will turn into a solid well before 0 degrees. 2/3 of the earth is covered in water, and I tell you that because also 2/3 of almost any organism's body is composed of water, and that's not a coincidence. The properties of water that keep the earth warm are the exact same properties that keep your body warm. Your body heats and cools itself by water, and so does the earth. So a little bit about the chemistry and the unique properties of water that make it so important to us. Water has the ability to form hydrogen bonds. Obviously, hydrogen is going to be involved, but what is a hydrogen bond? It is a weak transient bond, which means, again, weak, it's not very strong, it's easily broken, and it's transient. If something is transient, it's here, then it's gone. And then it's here, and then it's gone. That's a hydrogen bond. It's bonds, and then it breaks, because it's weak. It can't hold on. It's bonds, and then it breaks. Okay? So one hydrogen bond by itself is not very effective, but when they exist in large numbers, they can be incredibly effective. Okay? Hydrogen bonds are the reason almost anything will dissolve in water if you leave it there long enough. Okay? Might take thousands of years, but hydrogen bonds will pick it apart. The Grand Canyon, okay? The Grand Canyon used to just be a river, but over millions of years, it's hydrogen bonding that was picking at the soil as the water rushed by that carved out the Grand Canyon. Water can go anywhere, it can carve out anything, okay? And that's due to hydrogen bonding. If I walk up to you and I pinch you and then let go, okay, that's annoying, but it didn't do too much damage. But if I tell everybody in the class to come up and pinch you on and off and none of us stop for 1,000 years, okay, that's going to be really effective. That's exactly what hydrogen bonding is. When you have billions and trillions of water molecules all hydrogen bonding to something, eventually they will dissolve it. And here's an example of putting our salt crystal, which is what kind of compound? It is sodium chloride, but how are they held in association with each other? They are ionically bonded to one another. When ionic compounds are submersed in water, the hydrogen bonds in our little red sphere with the two blue spheres is water. Okay? They come up and they start to pick apart the bonds, the ionic association between sodium and chloride. And once they can get a molecule away from the salt crystal, they will surround it in what's called a hydration shell. And what this does is it prevents this sodium or this chloride from ever bonding to another sodium or chloride. The only thing it will be allowed to associate now is water. That's why if you put sugar, if you put salt in water and you watch it dissolve, you can sit that glass there for 1,000 years. You're never going to see salt crystals reform unless what happens? How do you get the salt back? You have to have the water evaporate or you have to boil it out. If you get rid of the water, then you'll get your salt crystals back. But as long as water is present, you will never see those crystals reform because they are surrounded on the atomic level by this hydration shell. Another characteristic of water due to hydrogen bonding is called surface tension. Water is attracted to itself. Hydrogen and oxygen, those molecules of water are going to be attracted to themselves, and they are going to form weak transient bonds through hydrogen bonds, and that's going to lead to surface tension. Okay? Surface tension is not a problem from human beings. We stick our finger through the water, we break the surface tension. But if you are a very, very tiny insect, you can skate along the surface of the water without breaking it. Okay? That's surface tension. Okay? Because those molecules have an attraction to each other, they're forming little bridges, and very tiny light objects can float along the surface of the water. Insects can move along the surface of the water due to the surface tension. 2 words to describe substances being attracted to each other. When molecules are attracted to each other, it's called cohesion. Okay? Remember that this is going to mean molecules of the same substance. Okay? Molecules of the same substance. When they're attracted, when water is attracted to water, that's cohesion. So surface tension is an example of cohesion. When molecules of a differing substance are attracted to each other, it's called adhesion. Okay? If something adheres to me, it sticks to me. Okay? When I walk out the door in the morning, dog hair is adhering to my pants. Okay? Dog hair is made up of one type of molecule, my pants of another, so it's adhesion. It's adhering to me. So 2 different substances, adhesion, the same substance, water being attracted to water, cohesion. Okay? The specific heat. And specific heat is a characteristic we use for many, many molecules and compounds, but as we talk about it here, we'll mostly be referencing water. So here's the definition of specific heat. The amount of heat that must be absorbed or lost by 1 gram of a substance in order to move its temperature 1 degree Celsius. Okay? 1 gram of a substance, so a few drops of water. How much energy do I need to put into that drop of water to get it to go from 3 degrees to 4 degrees, or 6 degrees to 7 degrees, or 20 degrees to 21 degrees? Okay? That is going to be the specific heat. And when we talk about energy, we're talking about calories. These are the same calories we're talking about when you think about food. Calorie is a measurement of energy. So when you look at the side of a box of crackers and it says there are 1,000 calories per serving, that's a unit of energy. That's how much energy you could extract from that food if you were doing that. Now, most of us eat more calories than what we need, so we then convert that calorie into something else, a type of stored energy, but that's essentially what you're measuring. How much energy could I extract from the food at the maximum? That's a calorie. Water specific heat is 1 calorie, 1 gram of water, 1 degree Celsius. So again, I have my few drops of water, I have my gram of water. I need to pump 1 calorie of energy into my 1 gram of water to get it from 4 degrees to 5 degrees, to get it to go up. Or I need to take 1 calorie of energy away from my 1 gram of water to get it to go from 8 degrees to 7 degrees. Okay? 1 calorie, 1 gram of water, 1 degree Celsius. That is the specific heat of water. This is twice what most carbon compounds are. Other carbon compounds need half a calorie of energy to move 1 gram of their substance 1 degree Celsius. Okay? So water has a very high specific heat. It actually takes a lot of energy in comparison to move water 1 degree Celsius. Why is that important? So if it takes a lot of energy, that means that water heats up very slowly. But if water heats up slowly, then water cools down slowly as well. This is the characteristic that allows you to maintain your temperature and the earth to maintain its temperature. So you first. What is the furnace in your body? What do we say produces heat for you? Your muscles, your skeletal muscles. They are specifically heating the water in your body. Okay? The energy that's released as heat from your skeletal muscles heats the water in your body. It brings your temperature up, and then your temperature will stay up because you cool off very slowly. That's why if you go to the gym and you jump on the treadmill and you're running, and you're sweating and you're heating up, as soon as you stop running, you don't just feel better, okay, and cool down. You remain flushed and sweating for quite some time after you get off the treadmill, because all the contraction of your skeletal muscle heated the water up, and then when you were done, the water in your body cools off very slowly. The same thing is true of the Earth. The reason that the Earth maintains a stable temperature is because of the water. The sun heats the water on the Earth, and that's what keeps us in a temperate climate. That's why if you live next to water, especially water that's close to the equator, you live in some place that's always warm, okay? Florida is closer to the equator, and it's surrounded on all sides by water, okay? You go farther down, parts of Africa, South America that run right next to the equator, those are the rainforests, the tropical areas. Why? Because they are right next to water that the sun heats all the time. So that's what determines temperature, is the heating and the cooling of water. Heat of vaporization, another characteristic of water. This one is the amount of heat that's required to change 1 gram of a liquid into a vapor or into a gas. So we saw a liquid go into a solid, and now we're seeing a liquid go into a gas. We saw specific heat was changing the temperature. We weren't changing forms. We were just changing temperature. Now we're changing forms from a liquid into a gas. For water, it's 586 calories. That's a lot. Calories are energy, and energy is heat. So, this is how your body cools itself down. When you sweat, you put water out onto the surface of your skin, then 586 calories of energy or heat break the bonds between hydrogen and oxygen and release it into a gas. Where is that energy or heat coming from? Who's providing the 586 calories? There's only two people or two objects in this equation, water and you. You're the one providing the 586 calories, because remember, energy is heat. The water takes the heat from your body, uses it to break the bonds, and goes into a vapor. If I take heat from you, you feel cooler. If I give heat to you, you feel hotter. Okay? So when you sweat and put water out onto the surface of your skin, it steals 586 calories of heat from you, breaks the bonds, and becomes a vapor. And that's why sweating makes you feel cooler, because it's just a chemical reaction that's taking heat from your body. More things that involve water. Hydro means water. And substances either like water or they hate it. Okay? They are either hydrophobic or hydrophilic. If you are phobic of something, what are you? You're afraid. A phobia is a fear. So hydrophobia is what? Fear of water. These are the molecules that do not like water. They don't want to interact with water in any way. We would describe them as hydrophobic. Substances cannot interact with water. These are lipids, fats, oils. They do not want to bond with water. We also call them nonpolar. The only other molecule they will interact with is something similar to themselves. If you put oil and water together, you can shake it and shake it and shake it. The oil will break up into smaller and smaller droplets, but as soon as you stop shaking, all the oil droplets find each other again, and they will only interact with each other. They will not interact with the water. That's called hydrophobic. Excuse me. Substances that can form hydrogen bonds with water are called hydrophilic. Philic or phile is to love something. Okay? An audiophile is somebody who loves music, who loves audio things. Hydrophilic is to love water. What's a substance that we've already talked about that can interact with water? Salt. Salt, sugar, anything you pour into water, you stir, it dissolves. That's a hydrophilic substance, also called a polar substance. Okay? It loves water, it interacts with water. Again, the way to tell if something is hydrophilic, if it easily dissolves in water, it's hydrophilic. Okay? If it won't dissolve in water, it's hydrophobic. All right, we're going to step away from water for a little bit, and we're going to talk about another chemical property that's important called pH. Okay? pH is defined as the hydrogen ion concentration of a solution. Okay? How much hydrogen ion is in it? Why does that even matter? Why do we even care? Okay? The amount of hydrogen ion in a substance determines how acidic it is. Okay? Very strong acids can be useful or harmful. The same for very strong bases. They can be useful or harmful. Your stomach, for instance, is a very strong acid. Your stomach acid is incredibly strong acid. So that's useful to you. So we express pH as the negative logarithm of the hydrogen ion concentration. And that's exactly what it says here. pH equals the negative logarithm. And anytime you see a chemical symbol inside of square brackets, that always means concentration of. Okay? If I have square brackets with a C inside, that's the concentration of carbon. If I put an O inside, it's the concentration of oxygen. In chemistry, square brackets always means concentration of. Negative log of the concentration of hydrogen ions. The logarithmic scale is what's called a base 10 scale. The scale that we're normally used to working in always goes up by 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I went up by 1 each time I named a new number. The logarithmic scale goes up by powers of 10, which means in order to move from one number to the next, you have to multiply by 10. So it goes 0, 10. 10 times 10 is 100, so 0, 10, 100, multiplied by 10 again, 1,000, 10,000, 100,000. Every time I move a number on the logarithmic scale, I have to multiply by 10. Okay, that's a base 10 scale. So, how do we express hydrogen ion concentration? We usually get it in its exponential form, okay? So, if I tell you that a solution has a hydrogen ion concentration, this marker is dead. One day I'm going to learn to bring my own markers down. If I tell you a hydrogen ion concentration is 10 to the negative 7th, that's its exponential form. If I want to write it out longhand, it looks like this. That's 10 to the negative 7th written out long form. Is that a lot of hydrogen ion concentration? No, that's not a whole lot of anything, okay? The easy way to figure out pH, I will always give it to you in this exponential form. And this would work. If you had a calculator, the same thing would happen. If you put in 10 to the negative 7th and you hit negative log, you would get 7. So here's what you do. If I give you the exponent, you take this number, negative 7. We need the negative logarithmic, and a negative times a negative is a positive. So the first thing you do is make this exponent positive. And then you take it out of its exponential form and bring it into a whole number. So the pH of a solution, if I give you the hydrogen ion concentration of 10 to the negative 7th, the pH is 7. Okay? What you cannot forget is that this scale is logarithmic. So if I give you 10 to the negative 6, what's the pH? What's the difference between a pH of 6 and a pH of 7? It's 10 times. One is 10 times stronger than the other, and that's because of this. If we remember back to learning our decimals, each one of these is a tens place. Tens, 100, okay? So every time I move an exponent, I'm moving one direction this way or a tens place that way. So the tens is always going to come to haunt you no matter how you look at it. Okay? What I want to look at is this, the pH scale. Because here's your exam question. I'm going to give you a concentration of a few solutions in exponential form. Solution A is 10 to the negative 4. Solution B is 10 to the negative 12. Give me their pHs and then tell me if they're acids or bases. The pH scale goes from 0 to 14. From 0 to 6 is considered acidic, which means a very high or a higher hydrogen ion concentration. From 8 to 14 has two words to describe it: alkaline or basic. And this means a lower hydrogen ion concentration. This is counterintuitive at first. Lower numbers mean higher hydrogen ion concentration. Higher numbers mean lower hydrogen ion concentration. And that's because you can't forget we're working in negative exponents. So 10 to the negative 2 is this, 0.01. 10 to the negative 12 is this. Okay? This is a much higher concentration of hydrogen ion concentration than this is. So again, it's counterintuitive at first, but you can't forget you're working in negative exponents. Higher the number on the scale, the lower the hydrogen ion concentration. The lower the number on the scale, the higher the hydrogen ion concentration. Substances that hover around 7, a little bit below, a little bit above, are called neutral. Okay? That is the key for most biological substances and organisms. Your blood, the fluids in your body, most of them hover around 7. There are exceptions, of course. We've already named your stomach acid. But for the most part, overall, you must always maintain a pH in your body of 7. If you go too high or too low, either one can result in death. So if we look at some common substances which I want you to be familiar with for the exam, I want to be able to list things like, I always want to say pop, you guys don't call it pop, soda, Coke, lemon juice, coffee, ammonia bleach. I should be able to make a list of the things you see on this chart, and you should tell me they're acids, they're bases, or they're neutral. So let's look in the acidic range from 0 to 6. Hydrochloric acid, okay? Your stomach acid, lemon juice, vinegar, cola, beer, tomatoes, coffee. Rainwater as it falls from the sky will be slightly acidic. Notice we're approaching 7. We're seeing urine, saliva. Right at 7 is pure water. Pure water is called deionized water. Okay? All the ions have been either removed or neutralized in deionized water, and that's at exactly 7. Your blood, right around 7. So we see bodily fluids and pure water hovering right around neutral. If we go towards the alkaline range, seawater, baking soda, Great Salt Lake, ammonia, bleach, oven cleaner, sodium hydroxide would be the complete opposite of hydrochloric acid. One is incredibly basic, the other one is incredibly acidic. So be familiar with this chart with common substances. If I were to give you hydrogen ion concentrations, you should be able to give me the pH and also tell me whether that solution is an acid, a base, or neutral. Questions on that before we move off pH, because that will be a part of your exam. Okay. So, how does my body keep my pH at 7 if all I do all day is drink coffee and soda? I'm just dumping acid into my system all day long. How am I staying at 7? Buffers are the way that you stay at 7. All living cells usually have buffers because they need to exist right around neutral. The chemical reactions of life, okay, all the chemical reactions that go on in your body produce different acids and bases. The stuff that you eat, different acids and bases. They're always challenging the pH of your body. So what buffers do is they keep the pH steady by either storing or giving up hydrogen ions when they are needed. Here's an example of a buffer. So, on the left we have the pH scale from 0 to 9. Okay, down on this end we would call it what? Acidic. 7 is, and then above, basic or alkaline. This system, whatever it is, wants to stay between 4 and 6. That is the target pH. we are going to start adding base. So we are going to make the solution more basic or more alkaline. The solution starts at 3. We begin adding base. We add 1 unit of base, and we can get it up to 4. Now, if there were no buffer present, this line would go straight up, right to here, okay, in a straight line. But what we see is as we add base, we're able to keep it in the range we want because of the buffer. Eventually, we exhaust our buffer. Our buffer can't give or store any more hydrogen ions. It's exhausted because we've added too much base, and then the pH shoots off the chart. But as long as we don't challenge it too much, the buffer can always keep us in range. In this case, in the range of 4 to 6. Where is your body's buffering range? What are you trying to keep around? Right around 7. Your buffers keep you around 7. Here is one of the most prolific buffers in your body. And I'm just introducing it to you now to plant a seed. You are going to eat, live, breathe, sleep this equation in 202. But for now, I'm just introducing it. 2 very popular substances in your body, water and carbon dioxide. Okay, they're everywhere. Water and carbon dioxide in your body can combine to form something called carbonic acid. It's got 2 little hydrogens here, and that's really what you want to focus on, are these 2 little blue spheres. Those are your hydrogens. Notice each one of these arrows is reversible. This equation can go to the right or to the left. Once carbonic acid is formed, it can go into something called bicarbonate and a free hydrogen ion. The important thing to remember about pH is that it's only a concentration of free hydrogen ion. If hydrogen is bound to another molecule, it does not count towards pH. So all the hydrogens that go into the water of your body do not count towards pH. If it's bound into carbonic acid, it does not count towards pH. The only way you can get more hydrogen ion is if it's free. So remembering that this equation can go to the right or to the left, let me ask you a question. You are too acidic. You have way too much hydrogen ion floating around in your blood. According to this equation, how would your body compensate? How would it bring your pH back down to normal? You have too much hydrogen ion. So would hydrogen ion combine with bicarbonate to make carbonic acid, or would carbonic acid make bicarbonate and free hydrogen ion? The free hydrogen ion that's floating around in your blood that you have too much of would bond to bicarbonate and go into carbonic acid. Does the hydrogen contribute to pH now? No. Once it's bound into a molecule, it no longer contributes to the pH. So let's do the opposite scenario. You are alkaline. You do not have enough hydrogen ion floating around in your blood. How do you get hydrogen ion out of this equation? What has to happen? The carbonic acid in your body must turn into bicarbonate and release a hydrogen ion. So if you are basic, this equation tends to go to the right. If you are acidic, this equation tends to go to the left. Okay? This is how you buffer yourself. Your body can make or break carbonic acid and bicarbonate ion to either give you hydrogen ion or bind it up. That's how you stay balanced. That's how you can drink coffee and drink Coke and eat tomatoes and drink lemon juice all day long and put all this hydrogen ion in your body, and your body will take that hydrogen ion and just bond it up into carbonic acid so that it doesn't hurt you. Okay, again, I'm not going to harp on this too much on the test, but believe me, it is definitely coming back to haunt you. No, this is an equation that happens in your blood. It's just a buffer, yeah. Okay, I'm going to take this out right now. I always have this bottom point, and it's from a different textbook, so this does not apply. And if you have your set of notes with you, you can take it out. All right, I always forget to do that. So now we are going to start talking about molecules that are important for your body, macromolecules. So what's a macromolecule compared to a regular molecule? It's a larger molecule. Remember that macro means large. Let me just check how much time I have left. Good. So, as we've talked about several times, you are made of carbon. Your favorite energy source is carbon. It's carbon all the time. No matter what we talk about, even with these macromolecules, it doesn't matter if it's a protein, if it's a nucleic acid, there's going to be carbon in it somewhere. Carbon is the biological framework for all of the molecules in your body, built by your body and used by your body. At the very base, we will always find carbon. You are a carbon-based life form. Macromolecules, again, large, complex assemblies of molecules. And in your body, they break down into 4 main categories: proteins, nucleic acids, lipids, and carbohydrates. Again, carbohydrates is the most obvious carbon one, but they all have carbon bases. Okay? It doesn't matter what they are, we'll find carbon in all of them. If we're talking about all 4 molecule groups, we have to make macromolecules and we have to break them. Making and breaking any macromolecule group happens the same way. Okay? If we want to make one, here's a 2-carbon molecule and a 1-carbon molecule. If I want to make them into a larger 3-carbon molecule, it happens by something called dehydration synthesis. When you're dehydrated, what have you lost? Water. Dehydration means loss of water. When we look at here, look, there's an OH, which is called a hydroxide, and hydrogen. 2 H's and an O. That's water. They bond together and leave as water, and then what's left, the 2 carbons, they bond to each other, and that's how we build a more complex 3-carbon molecule. Dehydration synthesis. If you synthesize something, you make it. Dehydration synthesis means making something by losing a water. Okay, that's exactly what those words mean.
On the second one, do they just combine together if they left H2O also?
Which one? This and this? These won't bond to each other, but what they will be available for is if then maybe over here I could pencil in another 3-carbon molecule, it could use this hydrogen for bonding. So these 2 are available for the same exact kind of bonding, but in this example, they won't bend around and bond to each other. But they are available for bonding with other molecules that might come in. Okay? We disassemble all macromolecules into smaller parts in the same way, and it's the exact opposite. Here's our more complex 3-carbon. We bring a water in, we break it in half, an OH goes to one side and H to the other, and now we've broken it into 2 separate molecules. That's called hydrolysis. Hydro and lysis. Hydro means what? Water. Lysis is something we'll see again and again and again. Lysis means to break or to burst. Okay? If I lyse a cell, L-Y-S-E, if a cell lyses, it bursts. Okay? And we're going to end up talking about that in cell biology, but lyse is a word, and lysis you will see in biology again and again and again, and it means to break or to burst. So hydrolysis, or hydro and lysis, means to break a water. So if I'm building, I'm dehydrating, I'm getting rid of a water. If I'm breaking, I'm bringing in a water, and hydrolysis, I break it or I burst the water in half. Okay, polymers. The word polymer. Poly means many, okay? If you are poly anything, you have a lot of whatever the word that comes after it, okay? Mer is an incredibly generic word that means unit, okay? Many units. We don't say what those units are. We don't say whether they're amino acids, carbohydrates, fatty acids. We're not saying. We're just saying there's a lot of units. So that gives us the definition. A polymer is a long molecule that's built by linking together a large number of small similar chemical subunits. A lot of smaller units. That's all polymer means. Okay? We're used to thinking of polymers with plastics and whatnot, and it does apply to plastics, but that's not the only thing it applies to. Here are examples of the monomer. What does mono mean? One, and so polymer is many. The monomer and the polymer of the 4 macromolecule groups. Okay, here we are with proteins. Okay, the monomer is an amino acid. The polymer is a polypeptide. Of course, and then we have the intermediate filament, which is the cellular structure, the macromolecule. The nucleotide is the monomer for nucleic acids. The polymer is the DNA strand. The cellular organelle is the chromosome. So we're starting to see those hierarchy levels build on top of one another. Here are the last 2 groups. Fatty acid is the monomer. Fat molecule, a triglyceride, is the polymer. And then adipose tissue is your organelle. Monosaccharide is the base for a carbohydrate, the monomer. A starch is the polymer, and the organelle could be a starch grain in a chloroplast. So that's the breakdown of the 4 macromolecules, their monomer, their polymer, and their organelle. We will stop there, and we will pick up with proteins on Thursday. Actually, if you guys hang around just a